So let's look at another example and see if we can practice sketching this particular function. So here I have the function x squared plus 3x minus 10 over x squared plus 8x plus 15. If I want to look at my steps, the first thing I want to do is see if I can factor it and then reduce. So I've got a quadratic in the numerator and the denominator, so let's go about factoring those two places. So the numerator is going to factor into an x and an x. I have a negative sign here, so I have a positive and a negative. So I'm looking for the factors of 10 that subtract to give me 3. That would be a positive 5 and a negative 2, because negative 2x plus 5x is a positive 3x. Now what's the denominator going to factor into? I have an x and an x. So here I have a positive sign, so I know I'm going to have two pluses down here. So what are the factors of 15 that add to give me 8? That would be a 5 and a 3, because that's positive 3 plus 5 is a positive 8. Now that I have my rational function factored, I would reduce in order to go on with the function. I want to stop here and just kind of remind you about one thing though. When I have my function factored like this, what if I were to ask you, what's the domain of this function? Well, it helps when I'm talking about the domain to take the denominator, right? The domain is all about what values are allowed in the denominator. And since my denominator is now already factored, it's easy for me to be able to say, well, x can't be negative 5, and x can't be a negative 3. So those are the two values that I would not be allowed to have in my domain. Those are the ones that I'm going to have to throw out. Every other value would be valid. So if I wanted to ask you what the domain of this function was, it would be x such that x cannot be equal to negative 5 and negative 3. Now going on with just graphing the function. So let's go back over here. Now that I have my numerator and my denominator factored, I can cancel my common factors. This gives me the new rational function f of x is equal to x minus 2 over x plus 3 that we are then going to be using throughout the rest of our process here. But what happened when I canceled this factor out, this common factor? Well, we talked about this in an earlier video, that when I cancel a common factor like what we have here, and I'm going to go over to the side, that x plus 5 factor that we just canceled tells me that I have a hole when x is equal to negative 5, because negative 5 plus 5 is 0, right? So I have a hole that's occurring there. It's not enough to say that we can't just cancel this factor off and say, it doesn't exist anymore, because in fact it actually creates just a single hole in my graph. Now because I have a hole in the graph, which is represented by a point on the graph, I need to know what is the y value then when x is equal to negative 5. So I'm going to take my new simplified function right here. The f of x is equal to x minus 2, x plus 3, rational function that I simplified, and I'm going to plug in negative 5 for x. So I get negative 5 minus 2, negative 5 plus 3. So negative 5 minus 2, change. That gives me negative 7 in the numerator and a negative 2 in the denominator. And a negative over a negative is actually a positive. So in other words, when x is negative 5, y is going to be positive 7/2. And that's the point where I have a hole in my graph. And we're going to need that in a little while. That was a lot of segues there just by factoring and reducing, but we needed to be able to talk about that. So for the rest of this problem, we're going to be looking at my rational function of x minus 2, x plus 3, the reduced fraction. Now we're going to talk about symmetry. Remember, we're going to replace x with a negative x and see what happens to the resulting fraction. So I'm either going to get a negative x plus 2 over x plus 3, because that's the change in signs for the numerator, or I get x minus 2 over negative x minus 3. So those are the two choices I'm looking for odd symmetry. So f of negative x would be negative x, so I'm plugging it into this up here, negative x minus 2 divided by negative x plus 3. That's neither of these two cases. So I have no symmetry. Okay, and that's all that told us. Now let's talk about the x and the y intercepts using, again, this reduced fraction. When I find the x-intercepts, that's where I set the function equal to 0 and solve for x. So we're going to take x minus 2, x plus 3, set it equal to 0, and solve. So I can multiply both sides by x plus 3, and I end up with just x minus 2 is equal to 0. And then add 2 to the right-hand side, x is equal to 2. So I have an x-intercept at when x is 2, y is 0. That's where I have an intercept occurring. Now my y-intercept is when I let x be equal to 0 and solve. So let's write it as this. Y is equal to x minus 2 over x plus 3. But I'm going to replace x with 0. 0 minus 2, 0 plus 3, or negative 2/3. So when x is equal to 0, y is equal to negative 2/3. That's where we're crossing the y-intercept at. Once we know the intercepts, the next thing we do is find the asymptotes. We have vertical asymptotes. That's where the denominator is equal to 0. So just to scroll up here, remember this is the function we're using. The denominator here is x plus 3. Set it equal to 0 and solve. I have a vertical asymptote then at x is equal to negative 3. Now we have either horizontal or slant asymptotes. Okay, horizontal or slant asymptotes is where we evaluate the degree of the numerator versus the degree of the denominator. So let's just rewrite my function so we can see it on this screen. F of x is equal to x minus 2, x plus 3. Well, the degree of the numerator is 1, and the degree of the denominator is also a 1. So they're equal. When the degrees of my numerator and denominator are equal, we take the coefficient that's in front of my leading term. And we say that y is equal to 1 over 1, or just 1. So I have a horizontal asymptote now occurring at y is equal to 1. Okay, I'm ready to now sketch what it is that I know. Okay. I know that I have vertical asymptotes, so I'm going to go ahead and mark off my graph here real fast. Okay, I found above that I have a vertical asymptote when x is equal to negative 3. So I'm going to come here at negative 3 and I'm going to draw a dotted line vertically with x is equal to negative 3. I had a horizontal asymptote when y was equal to positive 1. So we'll just go ahead and put that on here as well. So y equals positive 1. I had an x-intercept occurring at 2 zeros, so over 2 up 0, so we would have an x-intercept here. And I have a y-intercept occurring at 0, negative 2/3. So we're just going to sketch it. It's about right there. Now the other thing I did have was, remember that hole that we calculated? We had a hole at negative 5 and 7/2. Well, that's 3.5. So I'm going to go up, if I can follow this line right, to 3 and a half, and I'm going to draw a circle right there because I have a hole in my graph. Now remember, once we get the intercepts and the asymptotes on my graph, I'm going to go now put this into my calculator, which I've already done. When I put the function in my calculator, whoops, that's the wrong thing. When I put the function into my calculator, I went ahead and graphed the entire function. I could have graphed the reduced function because they're exactly the same thing. But I want you to see that by graphing the entire thing, I actually find that hole, now that I say that, because this is the coolest thing on my calculator with this operating system. You might have a TI calculator, but it may not show this hole up if you don't have an updated operating system. But you can see that how there's this little blank spot up here. Well, that's the hole that occurs when x is -5, because it creates a 0 in my denominator, and remember, we can't have that on a rational function. So in this particular operating system, you can actually see it. Most of the time, you won't ever even see that there's a hole on your graph. Your calculator will just graph it as if it was really a solid line. So this is kind of unique, but you get an idea of what my function looks like. So now we're going to come back over here, and I'm going to sketch the rest of what I have. So I have a curve here, right? It doesn't have to be pretty, but that's what I have. And then I have this curve here passing through my intercepts and moving off like that. Now, I'm not going to ask on this one for some additional points because we've already spent a lot of time with the hole and everything else. But this is a sketch of my function. We already talked about the domain of the function, and we had holes in our function as well.